zemass. So now we're going to be looking at the Mars semi-major axis. The semi-major axis is half of the longest diameter of an ellipse, and also a semi-minor axis is half the shortest diameter of an ellipse. And with the diagram, this diagram shows Mars' longest and shortest distances from the Sun, which the longest one is the aphelion, which is mu, and the shortest distance will be the perihelion, which is eta. And you can see the values there: 1.38 astronomical units, which is 207 million kilometers for the perihelion, and 1.67 astronomical units, or 249 million kilometers for the aphelion. And we're going to make Z our semi-major axis for the following calculation. So as you can see, we have our Z, which is the semi-major axis, which is equal to the sum of the aphelion and the perihelion over 2. We will see that even with the other calculations that we did previously on Pluto and with the dwarf planet series. So that will be equal to 1.666 plus 1.381 over 2, and that will be equal to 3.047 over 2, and that will be equal to 1.5235, which is approximately equal to 1.52 astronomical units, or 228 million kilometers, correct to 3 significant figures for accuracy. We always talk about this accuracy from the premature approximation and the final approximation of the answer. Now we're looking at the Mars orbital period, which is the time it takes to move around the Sun, to go around the Sun. As you can see in the diagram on the top left corner there, which shows Mars in orbit around the Sun, that white path is the orbit, and the Sun is clearly labeled. This is not to scale, of course the sizes are not to scale, as you can see. So the note at the bottom says, according to Kepler's third law, we're going to use this law in the calculation, which states the squares of the orbital periods of the planets are directly proportional to the cubes of the semi-major axis of their orbits. So like we say, the semi-major axis is the longest diameter of an ellipse, or of the orbit. So we're talking of the cubes of that semi-major axis, and then we are also looking at the square of the orbital period of the planets, or the orbital periods of the planets, where in this case we are not dealing with two planets, we're dealing with the Sun and Mars, which is a planet. So it's just the two bodies. Let's use the word bodies. So with this in mind, let us now derive the equation that we're going to be working with. So as you can see, the square of t is basically the square of the orbital period. So the orbital periods will be represented with the symbol t, and the r will be the separation of the masses, or what we call the semi-major axis of the orbits, which is that longest diameter of an ellipse, or longest diameter of the orbits, which is r, and that will be cubed according to Kepler's third law. So that relationship is proportional, and then we derive the equation by just rearranging. It's basically just rearranging the equation so that we make t the subject of the formula. As you can see, it's clearly outlined. If you don't understand, you might need to visit the one on the video on series. We try to explain all of that. So we then get our t is equal to 2 pi multiplied by the square root of z cubed over gm, where g is the gravitational constant and m is the mass, the larger mass. The capital letter M represents the larger mass, which is the mass of the Sun in this case. So by substituting the variables with actual quantities and converting the period to years, the years will be the earth years. So t will be equal to that expression that we derived from the Kepler's law, and then that will be equal to 2 pi multiply the square root of z cubed. Our z is the semi-major axis, which is 227 million kilometers, as you can see with the number there, but it should be cubed, so that's why we have that 3 at the top there, and then to the power 3, and then the denominator consists of the g, which is equal to 6.674 times 10 to the power negative 11 multiplied by the mass of the sun, which is 1.99 times 10 to the power of 30. It's not so clear, but it's 30. And then we get our answer, which is 59,332,033.46. That will be in seconds. So when we go step by stage with the conversions, we have to divide those seconds by 60 seconds and then by 60 minutes, so that we get the minutes. But a shortcut will be multiply the 60 seconds by 60 minutes, because we want to find the number of seconds, the amount of seconds in 60 minutes. So it's 60 seconds times 60 minutes, which is 3,600 seconds, as you can see. So we then divide those 3,600 seconds into the number of seconds that we have found, the t in seconds, and then we get 16,481 point blah 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 hours. And then I want to find how many days can we find in those hours, and we then divide those number of hours by 24 hours, since 24 hours consist of one day, and that will give us 686.71 blah 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 days. And then we divide that number of days into years. So the easiest way to do it is by dividing those number of days by 365 and a quarter days, since we already know that's the amount of days in 1 year. We just use the normal year, not the leap year. I think I explained that in the series video, the video for the dwarf planet series. So then divide that and we get 1.88 years, correct to 3 significant figures, that for approximation. So basically what we're saying here is it takes approximately 1.88 years for Mars to make a complete revolution around the sun, or a complete orbit around the sun. So now I want to see at what speed is this object going to be moving around the sun, which is what we are going to call Mars orbital speed. So how we are going to find the speed, we need to combine certain equations. I remember I talked about it in the series video, but I just said you can try your own to try and derive the expression to calculate average orbital speed. And I think I said velocity. My correction there, it's supposed to be speed, because we are dealing with linear speed there. As you can see, to find linear speed, one of the stages there. So we need to find this speed, but it will be hard to find it without deriving an expression. Otherwise we'll be going in circles. We just need something straightforward, something easy to use. So to derive this expression, we combine two forces, rather two equations for two forces. The first one is the one that Newton suggested in the Newton's law of gravitation, which is the one you see there, called gravitational force. And this law talks about how the product of those two masses, the mass of the Earth and the mass of Mars, in our case, will be directly proportional to the square of the separation of those masses, which in this case we are calling the square of the semi-major axis, as we will see later on. So then find that will be the expression there. Then the other force we're going to combine it with will be the force of accelerating the object as it moves in that circular path, or that orbital path. And we find that that's what we call centripetal force or accelerating force, but usually we use centripetal force, and that is F subscript C is equal to mv squared, which is the mass of the Mars, which is the one that's in motion. V is the speed at which it's moving, squared over the separation of the masses of the Sun and Mars. So what we use here is what we call simultaneous equations in mathematics. It's basically simultaneous equations. As you can see, Fg is equal to Fc. And then we find that it will be basically gmm over r squared, which will be equal to mv squared over r. So if we were to look at a point, it means at this point both forces will be equal to each other. So now we're trying to find the v. We're trying to make it the subject of the formula, because that's our main objective in this stage, is to find the linear speed as stated above. So we then say v squared. So we then cancel the like terms. As you know, you rearrange those variables. They'll cancel each other, and that's what you see being crossed out in yellow there. And then we are left with v squared is equal to gm over r. Then we want to remove that squared, which means we have to put the square root sign there, as you can see in yellow. And then our final product would be, or the final expression would be v is equal to the square root of gm over r. And in our case, our average orbital speed of Mars will be given by v bar, where v bar is the average speed. And then the square root of gm over z, g will be the gravitational constant, m will be the mass of the sun, and z will be the semi-major axis, and that will be square rooted to find the v bar. So let us go to the calculation. So like I said, where g is the gravitational constant, m is the larger mass. In our case, it is the mass of the sun, which is the capital letter M, and z is the proposed separation between Mars and the sun, which is the semi-major axis. Let us find a v bar, which is the average orbital speed. So v bar will be equal to that gm over z square rooted, and that will be equal to, where g is 6.674 times 10 to the power negative 11 multiplied by the mass of the sun, which is 1.99 times 10 to the power 30, all over the denominator being z, the same major axis, which is 227,939,366 kilometers, and that will be equal to 24,139.48291 meters per second. And remember, I want to put it in kilometers per second because, hey, we don't want to deal with large figures, so we just want to scale it down. So we have to divide by 1000 so that we make it kilometers per second. If you want to make it kilometers per hour, you just then multiply what you get with 3600. But here we just want kilometers per second. We want to see how fast it is. So we say 24,139 point blah 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 divided by 1000 meters, because we have 1000 meters in kilo. Kilo means 1000, so kilometers is 1000 meters. So after dividing that, we get our v being approximately equal to 24.1 kilometers per second, correct to 3 significant figures, just for accuracy. So this is basically what we had for you in terms of the calculations and the figures, how we get the figures. So you just understand that it's not just guesswork, it's something mathematical and mechanical, so that we are very sure of what we are studying. Human beings on Mars. Can vegetation grow on Mars?